Hello students, in this video we are going to learn about power distribution scheme. So we know that in our mouse circuitry there are two components which contribute to the power dissipation. It can be a static power dissipation and the power dissipation can be due to dynamic change. So there are two components in power dissipation, they are static power dissipation and dynamic power dissipation. So what is instantaneous power? It is nothing but a power at whatever the time it may be. So I must get some power value. So P of t is nothing but what is P? P is equal to V into I. That is what I have written over here. So P of t is equal to IDD of t into VDD. VDD is the supply and the current due to the supply voltage is IDD. Now the energy consumed over time T. What is this energy consumed? We know that power is equal to energy by time. So if you do the integration of 0 to t because it is consumed over t. So 1 by t integral 0 to t into what is the value of P of t? We know that it is IDD of t into VDD into dt. It is nothing but it is a normal basic formula of your power as well as your energy consumed. Now I told that there are two components which leads to the power dissipation in your CMOS circuitry. So only if you know what are the various power components that is contributing to the power distribution, I can effectively work my circuitry. So now there are two components, that is static power. So what are the various reasons why my static power is happening? So there are three reasons. Because of these three things, the static power dissipation do happen. So it is caused due to the subthreshold conduction tunneling, which is gate tunneling, and because of the reverse biased diode. Because there will be a junction, that is a reverse bias PN junction that will be formed between your diffusion as well as your substrate. So because of that there will be a diffusion, and remember that in our previous videos we have seen about the leakage current about the memory. So those are nothing but it deals with the static and the dynamic power. So in specific in this video we are learning especially about the power. So for power distribution or power dissipation is happening because of three conditions: because of the subthreshold conduction, channeling effect, and because of the reverse bias diode. And these three contributes to the static power. Whereas by dynamic power is contributed because of the switching. What is that switching? We have a capacitance in the output side of a dynamic. See, I am talking everything in a brief way just because everything has been covered in our previous video. So in a dynamic circuitry, the output will be connected to a capacitor and the capacitor will be either charging or discharging. It is nothing but switching effect. So because of that charging and discharging of your capacitor, dynamic power dissipation do happen, and also there will be a short circuit current. When a short circuit current will happen, when both your NMOS as well as your PMOS turns on, there will be a path for your VDD to discharge towards ground. So in such condition, I can get a short circuit current. And now what is the total power? Total power is nothing but the static power plus the dynamic power. So now we see that we will see first about the static power, and then we will learn about the dynamic power and what are the ways to reduce the static power as well as dynamic power, and what is the effective power distribution scheme, how I can do various approaches through which my power is being reduced. That is, my power dissipation is being reduced in prices. So now see, in a static power dissipation, my quiescent condition, what is that? It is a steady state condition. When I don't give any input, my average power which is dissipated will be equal to 0. That's obvious. Because in static there is no direct path for your voltage to move towards ground. It will be either connected between VDD and your output, or else it will be connected between your output and ground. So when there is no input, there is no power dissipation, so P is equal to 0. But when your transistors are off, there are certain leakages that is happening because of subthreshold current. I'm not going into depth of the derivation of all these equations. That is beyond the scope of our subject. So we must know what are the reasons why the power dissipation is happening. The one is subthreshold current. What is subthreshold current? It is happening when your gate voltage is less than your threshold voltage. So what is the threshold current? It is given over, the formula is being given, which is IDS is equal to IDS of O into e power VGS minus VT divided by eta times of VT, which is thermal voltage, into 1 minus e power minus VDS by VT, where VDS is the drain to source voltage and VGS the gate to source voltage and VTH is the threshold voltage. Now see the next leakage current or the power dissipation is because of the reverse bias leakage current, which is ID, which is nothing but because it is a reverse bias, diodes will be there, a PN junction diode. So now because of that, there will be a dissipation, and the current which is dissipated is nothing but ID. ID is equal to IS into e power Vd by Vt minus 1. Okay, and one more participation, that is because of the gate tunneling. So the electrons do tunnel to the gate through the oxide. There will be an oxide. Through the oxide, the electrons are going to tunnel. So if I start to increase the thickness of my oxide, the tunneling will be reduced. It's obvious, right? There are electrons that has to tunnel towards the oxide thickness. So if I increase my oxide thickness, the tunneling effect will be reduced. So what is P static? P static is given by I static into VDD. It's so simple. So now how I can reduce a participation, that is static participation. See, we know that it is caused because of these three reasons. And now I'm going to reduce a participation. So what I can reduce, how I can reduce my subthreshold current? I can reduce the VGS, or I can reduce my VDS, or I can increase my threshold voltage, as well as I can do certain changes to my temperature also. So what are the things in which my subthreshold current will be reduced? I can reduce my VGS or VDS, and I can increase my threshold value. But if I increase the threshold voltage, what is going to happen? It will take a large amount of time for my transistor to turn on. So when it takes a large amount of time for turning on, the delay will be more. So as delay is more, the speed is going to reduce. And the next, what is the alternative solution for that? I can go for multiple threshold CMOS circuit. These things that we have covered previously in our previous video. Okay, so now the I static is nothing but the summation of the current due to the subthreshold conduction, tunneling current, and due to the reverse biased condition. So now we shall move into the dynamic participation, because usually the static participation will be constant because it is not dependent, or it is everything is due to the subthreshold current and the reverse bias leakage current and the gate tunneling. So what I can say that we have to do a lot of things, or steps has to be carried out for dynamic participation. So what is this dynamic participation? I told you already, there will be a switching power dissipation in your dynamic, that is causing the dynamic participation. So one charge plus one discharge. What is that one charge plus one discharge? If I give my input as 0, the load capacitance will be charged to VDD. If I give my input value as 1, it is going to discharge. The loaded or the charged capacitor is going to discharge towards ground. There will be a path for discharging, and it is given as 0. So this one charge plus one charge discharge. Okay, one time it is charging and another time it is going to discharge. So that there will be a path from VDD to ground. So to reach from VDD, that is for the VDD to reach to ground, there must be one charging condition and one discharge condition. So the capacitance, the load capacitance is switched between the VDD and ground. At what time? With an average frequency of switching frequency, which is FSW, which is at this particular frequency, my capacitor is going to switch between charging and discharging. So what is a charge which is associated with the capacitor? So the charge is equal to Cn into VDD. We know that Q is equal to CV. That is what I have written. Q is equal to the load capacity into the supply voltage. Now, the total charge that is moved from your VDD to ground in time t. Okay, so in time t, what I can say, the time t into the frequency into the charge. So at what frequency it is moving, and for how many number of period or the clock period I have to calculate. So t into switching frequency into the load capacitance into VD, because the charge multiplied by all your frequency multiplied by the time t. So with this I can find the value of P, that is a dynamic participation, which is nothing but VDD square into switching frequency into the load capacitance, where your switching frequency is depending on alpha into F. Okay, what is this alpha? Alpha is the activity factor. What does activity factor means? If suppose I have a clock and my clock is turning on one time and it is going off one time in one clock period. Okay, so that means it is rising one time and falling one time. So the activity factor is 1. And I have a clock period for 5 seconds. Okay, in that I have 4. In that 5 seconds, if I have only one time rise period, then it means My alpha, which is the activity factor, is 0.5, means how many number of times the activity is being performed. That is both your rise time and fall time. If both my rise and fall time is there for one time, then it means that my alpha is equal to 1. So I am converting my switching frequency based on alpha times of frequency f. So the dynamic participation can be given as alpha into VDD square into the frequency f into CL. That you know this, and this equation that you would have definitely studied previously. So now how I can reduce the dynamic participation? I can go for reducing the dynamic participation. We know that expression is VDD square alpha f into CL. So I can reduce f, or else I can reduce the capacitance, or I can reduce the frequency, or I can reduce the supply voltage. Now what is going to happen if we reduce all these things? We'll start with the alpha. So if I reduce the activity factor, what is going to happen? See, now alpha is nothing but it is related with the clock. How many times it is rising or how many times it is falling. So I want to reduce my alpha, means I want to make sure that my clock is not activated most of the time. See, usually in our CMOS circuitry, all the circuits will not be active at a particular time. Some circuits will be on and some other circuits will be off. But the clock is going for all the circuits. So I must make sure that my clock is not active by giving a clock as well as an enable signal. Okay, so now when my enable signal is turned on, what is this? Whenever my enable signal is on, which means whenever I want the particular circuit to turn on, I will give the enable signal. At that time only my clock will be ANDed with the enable signal, and that is going to give the gated clock, and the particular circuit is going to work. So I'm not going to turn, or I'm not going to use my precious clock for each and every circuit that are going to be idle. I will be enabling the circuit with, and the gated clock is going to make sure that my alpha is going to reduce. And what is the other way? So the other way of making the circuit is by reducing my load capacitance. So what is the load capacitance? Load capacitance are nothing but it is given as C intrinsic capacitance plus the input capacitance of the second stage. We will be having a load that is going to drive another inverter. So its capacitance as well as the intrinsic capacitance of my inverter will be there. So now if I go on reducing, I want to reduce my CL. So I can reduce the intrinsic capacitance as well as the gate capacitance. So if I reduce the intrinsic capacitance, it is causing some problem when I am doing the floor planning. So I can go for reducing the gate capacitance. If I reduce the gate capacitance, what is going to happen is, as gate capacitance is proportional to the width, if I reduce gate capacitance, my W is going to reduce. Now, what is the next thing? If I reduce my W, what will happen? We know that the drain current ID is directly proportional to W, that is mu and C ox W by L. So if the ID, that is the drain current, is directly proportional to W, and we know that I is inversely proportional to R. So if I reduce the W, what is going to happen? My R is going to increase. Okay, so which means that the delay, because R is increasing, tau is nothing but RC. So when I'm increasing my R, my delay is going to rise. So what is the problem when I am reducing my capacitance? If I reduce the capacitance, my delay is going to rise. And what is the other case that I can go? I can touch my VDD. The dynamic power is directly proportional to the VDD square. Okay, so if I reduce the supply voltage, definitely I can reduce the participation because it is squared. But actually what is happening? The delay tau is inversely related to VDD. So if I reduce the VDD, my delay is again going to increase. That is not our ultimate aim. So I can't even touch the VDD also. So I can reduce the frequency. So if my frequency is reduced, what is going to happen? Frequency and time are inverse related, and again my time is going to increase and circuit is again becoming slow. So now see, we can do some other method to reduce our VDD. So in power distribution scheme, I have three different approaches, which is static voltage scaling, multiple voltage scaling, dynamic voltage frequency scaling. So first thing is SVS, which is static voltage scaling, and the second is multiple voltage scaling, and third is dynamic voltage frequency scaling. So what is the first approach? I'm going to divide my circuit into different voltage domain, and I'm going to give for each particular domain, that is a domain will be having set of circuits inside. Consider there is a domain A, inside A there will be various circuitry. Now I'm going to drive all these circuits with a common voltage of 1.5 volt, for example. And I have divided the entire circuit into various domain A, B, C and D, and I'm giving the supply voltage, that is a fixed supply voltage, to all my domains. Okay, that is different supply voltage will be given. So there will be a set of circuits inside A, and those A circuit is going to operate only at 1.5 volt. Okay, now the voltage is fixed such that my performance is not affected. Okay, we are doing all these things. I'm distributing my power in such a way that my performance is not going to affect it. We know that power is nothing but V into I. So I'm doing certain steps so that my power is not being affected. So I'm distributing in such a way that all the circuits are getting the same fixed voltage. And I can make this with the help of feature size scaling. So I'm going to reduce the feature size such that all the device is going to get a fixed voltage. Now, the second type is called as multiple voltage scaling. So in multiple voltage scaling, all the voltage domain can have more than one voltage. Means in previous thing, I had only one set of voltage. Means I had in a particular circuit, it will be driven by a fixed voltage. Whereas in multiple voltage scaling, I can have voltage islands. Means there will be certain islands that will be reserved. See, I have written 3 circles over here. One has been driven by 1.6 volt, and this is the voltage of 1.7 voltage island, and this is 2 voltage island. These are the various circuitries, and this circuitry at one time may be in need of 1.6 volt, in another time it may be in need of 1.7 volt, or another time it may be in terms of it needs 2 volt. So what is the drawback over here? The output of one will be driving another. See, I have 2 circuits. Okay, consider this circuit and this circuit. Maybe this circuit is activating or working with a voltage of 1.6, and this circuit is working in a voltage of 2. Now these two, the output of this must be driving the another, which is at different voltage. So this is one of the drawback when I'm using the multiple voltage scaling for reducing my VDD. So for that, what I must do, I have to do a level translation. So when I want to use a level translator, it is going to be hardware circuitry, and because of this voltage islands and the various circuitry and the interconnections between all the circuitry, the floor planning becomes a tedious process. Now, another thing which is out of the scope is dynamic voltage frequency scaling. So this is nothing but the extension of multiple voltage scaling. So depending on the workload, I can change my voltage and frequency. Suppose my particular circuit is working more, I will not be touching the voltage and the frequency of that particular circuit. If suppose the particular circuit is kept idle, for that type of idle devices, I can monitor the workload and I can change or reduce the voltage and the frequency. So now I can reduce the voltage and thereby I can reduce the frequency such that my dynamic power dissipation will be reduced. See, the circuit which is a processor, that my processor is going to work, and there is a monitor, and it will be monitoring whether the voltage that I'm having or the task that the circuit needs lot of supply or not. If the supply is needed because of DC-DC converter, I will be getting a lot of supply, as well as a function generator will generate a lot of frequency. If suppose a particular task is of no use, then the monitor will sense that, and definitely the DC-DC converter is going to reduce the supply voltage, as well as a function generator will also reduce the frequency. So when the supply as well as a function is being generated or it is reduced, my dynamic participation will be reduced. So the overall in this video we saw what are the components that give rise to the dynamic participation as well as a static participation, and what are the ways in which we can reduce the dynamic as well as a static participation, and the power design, that is a low power design strategies for reducing the VDD was also learned. And I hope you understood this video. Thank you so much.